Breaking and Fixing Leakage and Content-Defined Chunking will be given by Kien Tuong and Matteo Scarlata. Welcome.
So Kien, I understand you really care about your new IKEA furniture, but did we really have to bring it with us on stage?
Well, I mean, I thought it was important. And anyway, well, thank you for helping me carrying these IKEA boxes that we have on stage.
Just in time. Okay. Hello, everybody, and welcome to Breaking and Fixing Content-Defined Chunking. This is shared work with Kien, Simon, and Kenny from ETH Zurich, and Felix from IBM Research Zurich. And I'm Matteo. And I shall find a pointer. So let's start with our puzzling title. You probably are wondering, what are all of these words? Well, let's start with chunking. What is chunking? It's the process of taking something very bulky and splitting it up in smaller chunks that are easier to manage and to transport around. Or to jump more in the computer science world, it's something like when you have a very big file, like a super HD copy of Big Buck Bunny, and now you want to split it in a lot of smaller chunks that are of smaller sizes. And why would you want to do this? Well, let's take the setting where maybe you have this file on your laptop and you want to transfer it on your cloud server. Well, instead of moving the entire file in one go, you can send the chunks separately. And so if something goes wrong over the network and one of these chunks gets lost, you don't have to restart again, transferring the entire file. You can just transfer the missing chunk. Okay, this is also another nice property of splitting things in chunks, is that if you have two copies of one file that are almost identical, they only differ in one chunk. So maybe you're working at the Blender Foundation and you have two copies of Big Buck Bunny that are almost identical. Well, you don't need to copy both of them over. You can only transfer the missing chunk, the chunk where they differ, and you also save a lot in your storage costs. Okay, so hopefully I convinced you that chunking is very useful, and that's why we see chunking everywhere. Say chunking in synchronization programs, in IPFS, in software patchers, like the League of Legends patcher. And naturally, we see chunking in backup programs, such as Borg, Restitch, and Babstash, but almost all of them. Okay, so how do we chunk? The most naive strategy for chunking is to do fixed side chunking. So we start from the beginning of the file, and then we count n bytes, and there we chunk. So for instance, with this example input file, we would obtain these chunks, one chunk per line. Can you see a problem with this? Well, if we just prepend a single byte to our source file, then we do the chunking process again. We start counting from the start of the file, and we cut new chunks. But as you can see, all of the new chunks are different from the old ones. This is highly undesirable because now we would have to transfer them all again, and we don't get any deduplication. So what we do instead is the second puzzling part of our title, content-defined. What do we mean by content-defined chunking? Well, we look at the source file and we define a window. So a small amount of bytes that we look at, and then based on this window, we compute a chunking predicate, pi. And now we keep like changing this window, sliding it over the file. This is what's called a rolling window. And we keep evaluating this predicate until we get an evaluation to true. And here we chunk the file. And as you can probably see, now the chunk boundary does not depend on the entire chunk being cut, but just on a local amount of bytes. Okay, so we keep doing this for all the other bytes in the file. And now let's try to do what we did before. Let's prepend a single byte to our file. And if we're lucky, the first window won't evaluate to true, and we will get a chunk exactly in the same position as before. What this means is that if we compare the original file with and their chunks and the file with chunk with the 1 byte prepended, then only one chunk will change, the first one. All the other chunks will stay the same. So now we solved all of our problems. We're happy. Everything is nicely chunked up in files. And yeah, we have all of our boxes lined up in storage. So Kien, what have you got there? What furniture did I even help you transport here on stage?
Oh, well, it's a surprise. It's a surprise for our office. So for that, I even removed the labels, so you can't know what's inside.
So I have no idea. But that box kind of looks familiar. It's like, that size, and these are a bit smaller. I bet that you bought a Kallax bookshelf.
Wait, how did you know that? Are you telling me, wait, are you telling me that without looking inside the box, from the size of the box, you can infer the content of the box?
That's it, exactly. So the size of these boxes is actually leaking something. And this is problematic, to say the least, when we combine content-defined chunking with encryption. There are only two possible ways to do this. One is we first encrypt and then we chunk. Well, why is this a bad idea? Well, functionally, that doesn't really hit our requirements. If your encryption algorithm is any good, changing the plain text will completely scramble the ciphertext. Therefore, like, your chunk boundaries will be all over the place. So what we actually do is first we chunk and then we encrypt. But now encryption has, unfortunately or fortunately, this property that it mostly doesn't hide lengths. So we can take a look at the sizes of the chunks, and this will tell us something. What do I mean by telling us something? Well, if we can see this length, then we cannot quite decrypt the chunks, right? We don't have enough information for this. But what if we break into the server of our target user and we can see these 3 chunks with these exact sizes? And now we cannot decrypt these files, but maybe we can make a guess. We maybe want to check whether our target user has some politically charged documents in their backup. How do we do this check? Well, we take the file, and then we can chunk the file ourselves. And then we will see which sizes of chunk we get out. And if we compare the sizes of our chunks to the sizes that we can see on the server, then we can guess that probably the user actually has that file. So chunking and encryption can be a very dangerous combination. How do we solve this? Well, this is where cryptography enters the game. We add keys to the chunking process. So this is such that given a file and a certain key, and a file and a different key, key prime, we obtain completely different chunks. And this means that more formally, we can define our predicate, what I called predicate, chunking predicate before. We call this window evaluation. It's a function that takes a key and the window as before. Now, as before, like, we roll this predicate, we evaluate this all over the file, and we still chunk where the window and the key make this function evaluate to true. What security would we want or expect from all of this? Well, probably I can convince you that if our window evaluation function with the key behaves like a Bernoulli distribution of parameter lambda to the -1, where lambda is the average size of chunk that we want to obtain, then an adversary could not infer anything by just looking at the size of the chunks. But what about the real world? Do we get this kind of security from keyed content-defined chunking schemes in the wild? I will let Kien tell you more about this.
All right, thank you, Matteo, for spoiling the surprise. Anyway, so let's see, what do they do in the wild? In general, applications that use key content-defined chunking require some performance. So in particular, we want some KCDC that preserves the rolling property that Matteo was telling you about earlier. That is, you can take an evaluation for a window and then compute the evaluation for the next window very efficiently, positively in constant time and not linear in the size of the window. On top of this, you have to remember that KCDC, the window eval function, has to be evaluated once for every window in the file. And that means in the order of 10 to the 9, 10 to the 12 times. So it must be blazingly fast. So how do you do this? You usually use some algebraic structure. Here's a sort of framework for how a lot of applications do it. In the while, you take a file that is going to be a sequence of bytes. And then you take a window of these bytes, and then usually they compute some polynomial. Maybe you don't see it right now, but you can trust me that this provides some rolling property. And I'm going to provide an example later. The second step is you take this polynomial, and then you compute a predicate on this polynomial. And if the predicate returns true, then you cut at the end of the window. Now, again, this is keyed. So in particular, both steps, both the computation of the polynomial and the evaluation of the predicate, can involve the chunking key. Let me make this a little bit more concrete by showing you how RESTitch, one of the backup systems that we analyzed, works. So RESTitch works something like this. We have a secret key. The secret key is an irreducible polynomial of fixed degree. Let's call this P. And it's a binary polynomial, so polynomial with binary coefficients. And we take a window, and we compute a polynomial Q over it. So you take a window B1, BW, so these are W bytes, so 8 W bits, and you interpret these as coefficients of a binary polynomial of degree then upper bounded by 8W. Now you take this polynomial Q, and you reduce it modulo P, the secret polynomial. And after that, you check whether the last K coefficients for some fixed K are 0. If all these K coefficients are 0, then you chunk at the end of the window. In other words, the condition is that Qx mod Px mod x to the K, that is, look at the last K coefficients, is this equal to the 0 polynomial? Okay, well, this has a lot of algebraic structure, and let me clarify that again. Every time we see a chunk, we get a polynomial Q, okay? A polynomial Q lives in a F2 vector space, gets passed through a linear transformation, which depends on P, the secret polynomial. So this is an unknown linear transformation, but then it gets mapped to 0. Okay, but then that means that every chunk that we see gives us a polynomial which lies in the kernel of this transformation. So after enough chunks, we can recover, with decent probability, a basis for the kernel of this transformation. Now, you have to trust me here that this is actually sufficient to recover the polynomial P. After you recover the polynomial P, then you know all the secrets that have been used for chunking. So now you can do fingerprinting again. We did not do this only for RESTitch. We analyzed other backup solutions. So we have RESTitch, Borg, Duplicacy, Babstash, and Tarsnap. For RESTitch, as I said, you only need to see some chunks. I did not put any other requirement. This is a known plaintext attack. So if we know that the user uploaded Big Buck Bunny, for example, then that is sufficient to recover the secret. For Tarsnap, we had to use a chosen plaintext requirement. That is, you give a file to the user backs it up, and you get the chunks out of that, even though they're encrypted. Anyway, we managed to break all of these. So these are the chunkers. The chunkers are broken, and so they go in the chunk yard. Now, we said that they want a KCDC which is efficient, but what applications in the wild actually want, we contend, is that actually the chunking decision should be pseudo-random in a cryptographic sense. Now, what this means is what Matteo said earlier. So you take a window and you run window eval on top of it, and then you get a decision bit B, whether you chunk or not. Now, this bit B, which depends on the plaintext, should be computationally indistinguishable from just tossing a coin of the appropriate bias. And because tossing a coin does not depend on the file, this says intuitively that window eval does not leak a lot about the file contents. Can we achieve this? The answer is yes, we have the technology. How do we do this? We do the same framework that we saw before. We take a window of bytes and we compute a polynomial, this time using the bytes as a coefficient, as coefficients. Concretely speaking, you take the bytes, or actually some mapping of the bytes into some field where your polynomial lives, and then you compute the polynomial using these bytes as coefficients. Then you can see that this provides the rolling property, because it is sufficient to, if you want to, say, remove b3 and add bn plus 1, to just multiply the polynomial by x, and then remove the higher term coefficient, and then add the new byte as the constant term. And this will result in a new polynomial, which is very efficient to compute and corresponds to the window just adjacent to it. Okay, now we take this polynomial and we evaluate it as secret point alpha. Alpha is going to then be part of our secret key. Then, instead of using the result of the evaluation, we pass this through a PRF. So the PRF has a key k. This is also going to be part of our secret chunking key. And then we compute the predicate over the result of the PRF. Now, intuitively, because it's the result of a PRF, it has some pseudo-randomness property, which gives us the property that we want, that it's indistinguishable from a Bernoulli. But the first part, actually, so all of these we can prove secure according to our definition, but the first part you might recognize as essentially being just a universal hash function. And this gives us a way to generalize this. We can just replace the first part with a universal hash function, right? So now we have the key for the universal hash function and the key for our PRF as our chunking key. But this is good news. So because we actually can prove, and we prove it in a paper, that Restich KCDC is actually not a secure KCDC, but it is a universal hash function. And this is great because it's good to recycle, especially furniture. So what we can do is we can just apply a PRF, say AS, on top of the Restich KCDC, and we get, well, we do get a slowdown, but at least it's secure. Now, this leads me to a final discussion. So it does incur a 1.5 times to 2 times slowdown. So this is not great, but is this actually necessary to prevent fingerprinting? To answer this question, let me go back a little bit from a slide that we saw before on the attack on Restich KCDC. And I said here, if we have enough chunks, so if we have exact knowledge about the chunks, we can recover the polynomial P. But sometimes there are some processes, for example, encryption, for example, padding, that does not give us complete information about the chunk boundaries. So if we look at the KCDC scheme, yes, it's broken, right? But a little bit outside of it, we have some noise. So our attack, for Restich in particular, requires very certain knowledge, very specific knowledge about the chunk boundaries. And if we don't have that, this actually kind of breaks our attack. So let's look at the chunk here again. The question is, what did we break? Did we break the KCDC scheme, or did we fingerprint across the whole backup system? Well, the good news for us is that actually our attack on the KCDC scheme actually extends to some of the backup systems. For example, Tarsnap, Restich, and Borg. For some of them, actually, the compression or the padding is so aggressive that we can't actually break it in this way. And we can't fingerprint files when we look at the entire backup system. So this leads me to sort of an open question. So we know that padding thwarts some of our attacks in practice, not all of them. So in some cases, this may be a sufficient maybe a sufficient mitigation to thwart all attacks under some condition. However, the problem is that we cannot capture this in our security model. Our security model concerns only the KCDC scheme. So here's an open question for you all. Can we come up with a security model that captures the security of a backup system as a whole, that includes encryption, chunking, compression, padding, deduplication, but at the same time still allows for efficient deduplication with efficient construction? And what I mean by this is that it's very clear that if you do fixed size chunking, you can leak very, very little, but at the same time, as Matteo showed earlier, this is not very efficient for deduplication. I'll conclude with a last open question for the community. Does anybody want some empty cardboard boxes for free? Thank you.
We have time for a question or two.
Can you say more on the threat model? Because when you say like the adversary can download the file and do the chunking itself, are you considering all the files adversary is confused with will be the same size? Because definitely adversary can know whether a particular file a user has just by looking at the size of the file. For example, if a particular file is 100 gigabyte, then adversary knows even whatever chunking you use.
Yeah. So our threat model for fingerprinting is maybe outside of like some of the traditional threat models. We assume that we know for certain that a file is in backup. So something like, I don't know, let's say that you're backing up your entire system, maybe some system libraries, something that we can use to like instantiate our attack. And then after we have instantiated the attack, we can fingerprint other arbitrary files. So we can take a big set of target files that we're interested in checking, is this file in the backup or not, chunk all of these interesting files, and then compare them with the chunks that we see in your backup.
So these interesting file has to be similar size, right? Otherwise, it's a trivial attack that, okay, if your one file is way too big.
Right. So for some backup system, yes, there would be a trivial attack. For some others, when you look at the chunk storage, you don't see file boundaries exactly. So like you can see a lot of chunks.
Oh, yeah. Okay.
But then like chunking actually helps you protect against exactly this kind of trivial attack where you can just look at the total size.
But the timing channel will leak the boundary, right? If you are interacting with the particular file only.
Second.
The timing channel, or you are saying only the backup?
Yeah,
it's like, okay.
timing channel to leak. Yeah, so there are a lot of subtleties in how much can we infer from just seeing the chunk, and how much can we infer from seeing the total size, like summing up the chunks.
So have you looked into if something can be done for the file to hide the file sizes, something similar to this?
Like
by padding, like by randomized padding or something?
Yeah, I think some padding scheme can help. But this is like, since our model couldn't capture this, so we don't have an official recommendation on how to fix this. Like we think that padding things with some efficient padding scheme like PADMI would help, but only in the presence of a strong chunking algorithm.
Okay, thank you.
We'll take one more question.
Yeah. So when you consider the storage system with modifications to files, it seems like fixed length chunking as a baseline leaks some information about this part of the file was changed, this part of the file wasn't changed. Does content-based chunking, even with the use of a secret key, amplify that attack?
So yeah, I think this is another bigger issue. So the presence of the duplication itself is another side channel. And so our analysis is very orthogonal to this. We decided to focus on the sizes of the chunks. But yeah, like a wider model would also need to capture all of the duplication and the time-based access pattern. This makes for a very complicated model. Becomes pretty unwieldy.
Yeah, this is essentially like the open question that we have here. Right? Really, can you capture everything about the system, like a backup system? We found it a little bit like there are a lot of difficulties in doing this, but we can discuss also offline if you want.
So something that we are sure about is that efficient deduplication comes at odds with security. So if you always deduplicate when you have the same chunk, then you will leak something to the adversary. And not deduplicating comes at a storage cost. So that's a trade-off.
Okay, let's thank our speakers again.